The topic of series convergence tests is a point where we bring together a lot of the ideas and techniques that have been discussed so far. And this is a very important and powerful idea because many of the functions that we're interested in can be defined in terms of series. We've seen that before. And we want to determine whether those series actually do converge to a value for a range of input values, or all, for example, all real numbers, or even all complex numbers. Now, the first idea is a test, and these tests are based on the sequence items within the series. The first test is the divergence test, which in fact indicates whether or not the series will actually not converge, or what we call diverge. If the terms in the sequence as part of the series are not themselves getting close to zero, then the sum of all those terms will never converge, it will diverge. But the opposite is not true. If the terms in the sequence that we're adding together to form the series are getting closer to zero, then that doesn't guarantee that the sum will eventually converge. And the classic example is the sum of 1 over n, where n is a positive integer, like 1 plus a half plus a third plus a quarter. That's the harmonic series. That series will diverge. So if the terms in the sequence that are used when added together to form the series, they're not getting close to zero, then the series will never converge, it will diverge. The next test is the ratio test. Is if successive terms in the sequence, we take the ratio between them, so a term divided by the previous term in the sequence of the terms that make up the series, and that ratio, we can work out its limit as we get more and more terms. If that limit is less than 1, then the series will converge. If the limit is greater than 1, then the series will diverge. And that makes sense because the terms are getting bigger. Okay. If the ratio, its limit is equal to 1, if we can calculate that limit, then it's inconclusive. We don't know whether the series will converge or diverge. We don't know directly from this test what the limit will be, but it will tell us whether or not the series will converge or diverge for L less than 1 or L greater than 1. The next is in some ways an obvious test. If we have two series where we can pair up terms in the series, the sequence terms, and we can show that terms in the series that we're interested in, A, are all between the terms in another series, B, and we know that B converges, then we know that the sequence of terms, that when we add them together, the series A will converge. Alternately, if we know that the sum of the terms of the sequence of A diverges, then because the terms in B are bigger than those in A, we know that the sum of the terms in the series B will diverge. And then we have an alternating series test. And here we have another test of, in this special case of where we've got 1 over n to the power p. If p is bigger than 1 and n is a sequence of positive integers, then that sum to infinity will converge. So for example, P could be 2 or 3 or 7.2. So adding all those terms together will eventually converge. If P is less than or equal to 1, such as a half, then the sum of the reciprocals of n to the power P will diverge. And there's a little test here. And we can see the sums that are diverging. We look at the graph, it's going up. And here is one, the series is converging, and P is greater than 1, and it's reaching a limit.